let's start.
So welcome back, everyone. Now we'll have Hans-Guenther Moser talking about searches for quantum decoherence at Belle and Belle 2. Please.
Okay. So first, thanks to the organizer that they gave me the opportunity to present our Belle and Belle 2 viewpoint. So, I mean, in contrast to many other talks, I'm more talking about searches for decoherence, because in principle we believe that at the Y4S we have an entangled state, and we use this to measure B0 oscillation frequencies and CP violation. But on top of that, we can think of, can Belle's inequality be checked? But on the other hand, I mean, if this is not completely true and we have some decoherence, how would that affect our measurements? And yeah, this I will discuss in detail. Okay, first, I mean, where are we? So this is the KEC-B and Super KEC-B accelerator located at Tsukuba in Japan, about 70 kilometers north of Tokyo. It's a rather small 3-kilometer circumference E+ E- collider at the about 10 GeV center of mass energy. And KEC-B originally started in 1999 to 2010. And it was, together with the competitor at SLAC, very successful to establish CP violation in the B0 system, essentially confirming Kobayashi-Maskawa's theory. So now we are somehow upgrade, so it's not establishing CP violation, but measuring it with high precision to look for deviations. And so Super KEC-B has been upgraded to deliver at the end about 50 times the data a KEC has delivered, and by increasing the luminosity by a factor of 30. This will be achieved, or is achieved partially, by squeezing the bunch size down to nanometer dimensions. So this is for KEC-B, and you see it's about 1 micrometer. And this will be now 50 nanometer in the vertical directions, and also the others will be squeezed down. So this increases the density of the electrons and positons in the bunch and boosts the luminosity. In addition, we increase the beam current. Some note, I mean, the accelerator is asymmetric. So we have 1 beam 8 GeV and 3.5 GeV in KEC-B, and well, a little bit more symmetric in Super KEC-B, because otherwise we would not achieve the high luminosity. And the effect is that the center of mass system is boosted and moves along the beam direction with this beta gamma boost. Okay, the detector itself, just shortly, I mean, this is Belle. And in order to cope with a higher luminosity, we had to replace the inner detector, especially the silicon strip detector is now replaced by, at least in the innermost layers, by a high granular pixel detector. And yeah, then a new chamber. We have better particle ID now based on Cherenkov detectors instead of time of flight. Well, and the rest outside hasn't changed much. Okay, now to the 4S. I mean, you have seen here, this is when you collide electrons, positrons at around 10 GeV. So you see this series of resonances. The epsilon was actually, I mean, this was how the B quark was discovered. And then you have some radial excitations, and the 4S is the first one where the mass of the 4S is above the threshold for B0, B0 bar, and also B+, B- production. And it's just above the threshold, only 20, remaining energy is only 21 MeV. So there's no possibility to create B stars, for example. So it's in a pure B0, B0 bar state. And therefore it's entangled. So you have this wave function. So you have B0 at P, B0 bar at minus P, and vice versa in one wave function. Effectively, if one B decays, the common wave function collapses and the other B is in just exactly the opposite state. No uncertainty on that. So one B takes the state of the other B in the system. And just to tell you, when this happens, they are usually well separated. So the ratio between the flight distance or the separation and the radius of a beam meson 1 Fermi is about 5 × 10⁻⁻⁻, so rough. And they are also they are so separated that at least for most of the events, no light signal could go from one to the other. For some fractions, it could be the case, but for most of them, this is not the case. So again, and this is something really a present of nature to us, and this we can use to measure the zero oscillation frequency and CP violation based on this entanglement. But on top of that, how can we actually demonstrate this entanglement and even check Belle's inequality? And second question, how certain are we that the entanglement is always the case? Are there some effects which would collapse this wave function before the B decays? So for example, can the 4s decay in the 2b's and a soft gamma, which changes then angular momentum and the wave function and could lead to decoherence? Or might be there some kind of interaction with background fields, maybe beyond standard model, which also destroys coherence at a very fast time scale. And this is some worry because such effects could lead to systematic errors in our CP violation measurements. So we should consider that. So, but first I want to explain the B0 bar mixing. So it's like in the K0 system analog. So a B0 can transform with this box diagram, mainly by T-quark exchange, into its antiparticle. Well, if you treat that formally, you have to introduce, instead of these flavor eigenstates, weak eigenstates called B light and B heavy. And they are a linear combination of the flavor eigenstates. Usually this P and Q is 1 if CP is conserved. And as an effect, you get time-dependent oscillations from the B0 into the B0 bar. So you have the exponential decay, and then this 1 minus cosine delta MT term doing this oscillation. And the probability that it remains a B is just the complementary plus cosine thing. And delta M is the mass difference between the heavy and the low state. It's about 0.5 inverse picoseconds. Okay, so on top of that, we have CP violation, also due to the weak interaction. And this is a consequence of the complex phase of the Capito-Kobayashi-Mascara matrix. Usually, the parameterization is that this phase is in the VUB and VTD element, but yeah, this is convention. And CP violation happens if there is an interference between 2 or more decay amplitudes. So if you have an amplitude describing the decay of a B0 into a final state F, you have one with a weak phase and another amplitude which has a strong phase. In principle, both can have weak and strong phases, but you can always rotate them away, so only the difference counts. And for the antiparticle, you have to do the complex conjugate. Then the phase of the weak phase flips sign. The strong phase does not, because strong interaction conserves CP. And if you do the squaring and calculate the branching fraction, you see that these two things give you different results. This can happen either by interference of decay amplitudes, say a tree diagram and high order diagrams, or more important, by interference of mixing and decay. So if a B0 decays into a CP eigenstate, like shape psi k short, it can do so directly, or it can first transform in a B0 bar. Then you pick up this weak phase, and then the B0 bar decays in the same eigenstate. And then you also get this interference and a time-dependent CP violation, because the mixing is, of course, time-dependent. So what's the phenomenology and how does it look like in our experiment? So first, you collide E plus E minus, create the Y4S. This decays in the entangled B0 bar state, which propagates in time. Then suddenly 1B, we call it B tech, decays. and it decays in a state that we can deduce whether it's a B0 or B0 bar, because it's a semi-elliptic decay, for example. In practice, we use PDTs and neural networks to demand, but it's not important here. And at that point, we know that the other B is in the opposite state, and then it propagates, does this oscillation thing, and decays in the signal as a signal B in the state we want to select for our analysis. Maybe a semi-elliptic decay if we want to measure delta M, or if we want to measure CP violation, it should be a CP eigenstate like shape psi k short. And we can measure with our vertex detector the spatial separation between the two decays, and from the known boost, we can measure this time difference delta T. And this works. I mean, here are some recent analysis from Belle 2. So first the oscillation. So you have again this well-known cosine, and here we can calculate the asymmetry. So the difference between the mixed, the non-mixed and mixed state overall, which gives you just this cosine. And here you see this nice modulation. It's not ±1 because you have to take experimental effects in account, but this we know and can calibrate. Same for the mixing-induced CP violation. There we look in the golden mode, shape psi k short, and there the time dependence is a little bit more complicated. So you have a sine term, a cosine term with some prefactors. And for the shape psi k short, it turns out that this S measures essentially sine 2 beta, which is one of the related to the phase of the Kobayashi-Maskara matrix, and C is supposed to be close to 0. So if you make the asymmetry, you expect the sine wave, and that's also what you measure. It's asymmetry, and these are the individual decay functions here. So you see this shift, which is CP violation. Okay, but now can we use this effect to check Belle's inequality? And you can think of a classical aspect like experiment. Here you have the photons, you measure the polarization state. I mean, Alice and Bob does it. And then you build this correlation function at certain polarization angles, A and B, construct this S, and for, should be, has been shown below 2 for any local realistic model, and for quantum mechanics, 2 times square root of 2 for the optimal settings of these angles. And this has been, of course, measured to high precision. And now what happens if we replace the polarization by the state of the B and B0 bar? So we do the same experiment, but now we have one, Alice measures B0, B0 bar in one direction, Bob in the other direction, and this polarization angle difference we replace by the phase delta M times T, which gives you essentially the difference of the polarization. And this was somehow done 2003 by Apollo Go and collaborators, and they measured S equals 2.8 for these magic angles here. And hurrah. But it turns actually out that this has a problem, because if you introduce some non-QM model like spontaneous decoherence, so you assume the B0 and B0 bar are not in an entangled state, but the epsilon decays in separate states, B0, B0 bar, and they propagate independently without really knowing from each other. And then you do the exercise, build the correlation function, and you measure 2.3. So you can say, well, this is even higher, but this is definitely larger than 2. So something is wrong. And actually it turns out it's comes from the rather short lifetime of the B. The B decays mostly before it undergoes a complete oscillation. So you start with a B0, and then you slowly, this vector points more into the B0 bar direction, but it decays already here when delta M over gamma is above about 44 degrees. So it has still 72% correlation with the original state. And that is the same for the B0 bar on the other arm, which is phase locked. So if you do the calculation, they have a high correlation, even if they are not entangled, and this spoils this Belle inequality test. This has already been pointed out in a paper which shortly followed the Rowe publication. And the crucial parameter is this X, which is delta M over gamma, as I told you. And in order to make a Belle test, this should be larger than 2. And for B0, B0 bar, it's definitely smaller than 2. And for other meson systems as well, maybe the B sub S could be a candidate, but this has other problems. Furthermore, there are more problems discussed in this paper, and one is this conspiracy loophole. We rely on the random decay of both B's. And there's no reasonable way to actively determine this equivalent to this polarization angle difference, delta M times delta T. And so you can imagine that you have a kind of Laplace demon, or however you call it, who could tune some hidden parameters like the decay times T1, T2, and the decay time, so that you emulate quantum mechanics and Belle's inequality, but it's not quantum mechanics and it's local. And we have no practical way to close its loophole. So essentially, so far to the Belle test. But what can we do nevertheless? And the idea is we can still calculate effects of some decoherent models or local realistic models. Look how they modulate the time dependence and fit to the data. One model is this spontaneous decoherence. So the entanglement is lost immediately at t equals 0, maybe only for a fraction of the events with some decoherence fractions theta. Then there are other models, like one by Pompili-Celery, published here. It's a model based on local realism, but it reproduces the oscillation phenomenology, which has been well established, of course. It's a bit more complicated. It introduces 4 eigenstates for the B0, and yeah, can read the paper if you want. But it gives some predictions. And then there are some kind of Lindblad type decoherence models, and they introduce a gradual loss of coherence with time. And of course you have, I mean, it becomes important if the decoherence time is smaller than the D lifetime. If it's much smaller, we essentially recover the spontaneous decoherence. And if it's much larger, okay, then we can ignore it. Here it's just a picture how this would look like. So here again, you have the quantum mechanic entangled thing. So you have this entangled state, propagates in time, one B decays, and the other B decay starts exactly at this decay time here to oscillate according to this formula. So it starts 100% as a B0 and then gradually oscillates into the opposite state. If you have spontaneous decoherence, both start oscillating at the creation time, 0, then 1B decays, the first one, but it's not anymore in a B0, B0 bar state, but in a mixed state. So maybe 20% B0 bar and 80% B0 or whatever. So it doesn't tell you exactly the state of the other B. And the other B has already started oscillating before, so your time measurement is wrong. So you have 2 effects, mistake and wrong time measurement. And this modifies then the time dependence, I mean this cosine into this formula here. So in front of the cosine, you get a damping term and you get an additional phase shift or a sine term. And in using the standard values for delta M and gamma, you get a damping factor of 0.81, and the sine term has an amplitude of 0.24. If you look, I mean, in the decay distributions, how they look like, I mean, best is the asymmetry, so unlike minus like over all. in green, the quantum mechanical oscillation, and here the decoherent oscillation. You see the damping and you see the phase shift. Now, we should measure that. The damping is a little bit tricky to measure because it may be confused with the experimental mistake we have, so have to be careful. But the phase shift is certainly something we can measure with high precision. And this is for the mixing. Similar things occur in our time-dependent CP violation measurement. And then the damping would lead immediately to a wrong measurement of sine 2 beta. It might be compensated if we calibrate the mistrick properly, but okay, we don't know how this works. And it leads to crosstalk between the S and the C terms, so also some error. And yeah, can we actually say already something whether this is the case or not? And I mean, looking at existing data, we can look at the time-integrated oscillation probability. So you don't measure the oscillation frequency, but just the integrated number of flipped and unflipped events over the total. And there we can use the LHCb measurement as reference, because at LHCb, the B zeros are always in a decoherent state. There's no way that they get some entanglement because of hadronization and fragmentation. So this is a reference. And then we can measure if we have coherence R, this ratio should be this chi. If we have decoherence and both B's oscillate independently, we should measure a different value. That's the data. So this is if we have no decoherence, chi should be something like 0.19 or R, and then it increases as the decoherence fraction increases. Well, we haven't done a recent measurement. We can only use the measurements from Cleo and Argus decades ago. And it's in principle compatible with no decoherence, but the error is large. So in 1 sigma, it still allows for 10% decoherence. Another thing is again measuring, looking at the CP violation parameters, SCP and CCP, measured by LHCb and the 4S. And I mean, again, this is a standard formula, and we would then have this damping and crosstalk factors. So this would somehow deviate. And here is the average for LHCb. And for all the epsilon measurements, well, it's a big scatter, but again, the average is somehow has a shift, and epsilon is actually lower than LHCb. So for the C parameter, it's less clear, and they are more or less compatible. And here we have a 1.7 sigma difference. If I look at that, so this is the LHCb value. This is what we measure at the epsilon 4S. That is how it would develop if we increase the coherence. So we would also be compatible with some 10% decoherence. Yeah, I mean, there's a health warning. These are just my personal averages. I haven't taken into account correlations. In principle, the heavy flavor averaging group should do that, but they don't know about the problem yet. And here also the mistake could actually change the thing a little bit. So yeah, it's just to indicate what kind of to tell you what kind of indications we already have. Then there is a measurement actually has been done shortly after that by also Apollo Go and together with the Belle collaboration in 2004. So he wanted nevertheless to show entanglement, and they took Belle's most current analysis of CP violation and oscillation at that time based on 152 million dB bar pairs, but it's only a fraction of the final data set. Well, they selected this CP and flavor eigenstates in BT case with high purity, and here you see the oscillation pattern which from this data set. In order to make a clear measurement, there was further selection. So They used only the case of the B0 in D star lepton, where the lepton explicitly determines the flavor without error. And also the tech B was restricted to semi-leptonic decays, which gives you a high tagging efficiency. And you have this D star D0 decay, where you can reconstruct the mass difference with very high precision, so you can suppress any background to a negligible level. As a cross-check, they measured the B0 lifetime with this data, and the PDG value came out very well, so no bias. And then they tested different hypotheses, so the normal quantum mechanical prediction, the standard spontaneous decoherence model. This is this curve, which I explained before, with the phase shift and the damping, and then the Pompili-Celery model, which gives you actually a range of possibilities. Some are completely odd, and some are also quite similar to QM. And as a result, you see here the oscillation in the data. The yellow bands are the fit results, and above the pull. And QM, quantum mechanics, fits very well. Spontaneous decoherence is favored by 13 sigma, so really completely off. And even Pompili-Celery is disfavored by some 5 sigma and more. But if one fits a mixture of quantum mechanics and spontaneous decoherence, I mean, this is decoherence factor theta, some 3% plus minus 6% decoherence is still allowed. So summarizing, what do we learn? I mean, spontaneous 100% decoherence is certainly excluded, but there's still room for some up to, at the 1 sigma level, up to 10% decoherence. And actually, if you go through our CP violation measurements, this would lead to a shift of this SCP by 0.012. And now, in our latest measurement, the systematic error we quote on this SCP is 0.014. And so if we would take this seriously, this is the largest single systematic error in our measurement. Oh. Good, so what will we do? And we just started and got aware of this problem, but we certainly will repeat the Belle analysis now with much higher statistics. We have 4 times the data, better detector, more channels, better resolution, more refined analysis strategies. So certainly we can, I mean, limit or eventually see such an effect with much higher precision. We can even do more because we have a much better vertex resolution compared to Belle because of the smaller interaction region. So it's essentially in C, that's the direction the B0 system propagates. We go from 7 millimeter to 0.25 millimeter. The flight length is well about half of that. So it's not perfect yet, but at least we can make some kind of restrictions and limit the range of this T1, where the first tech decays. You can also use the transverse separation, which should be in the order of 50 micron, and we should have a resolution of 20 microns. So also there we could get some information. And this would add another dimension to our measurement. So if we have quantum mechanics, we are only sensitive to delta T and not to this decay time of the first B. With decoherence, this thing gets much more complicated. And yeah, we reach, of course, if we can do that, more discrimination power and can certainly make a better measurement at the end. It's actually some thought I had is if we limit the time for the first B0 to decay to a large value, we could actually overcome this problem with the lifetime. So then we measure only after the B has oscillated at least 1 full cycle and has randomized. So maybe then Belle inequality can be tested, of course, not closing all possible loopholes, especially not the active measurement. Okay, so now come to the end of my talk. Conclusions. I mean, turns out, unfortunately, that we cannot make an ASPE style experiment to check Belle's inequality. We do not have an active measurement. We depend on the random decay and also the short B0 lifetime, at least in the old measurement, leads to a violation of Belle's inequality, even if you have a local realistic scenario. But we can measure alternative models, fit them to the data, and at least exclude some of these models, or hopefully constrain them. But some tests at Belle have at least, I mean, they are still compatible with some 10% decoherent, and that's something we should check. And yeah, and because, I mean, this leads actually to a systematic error of our CP violation measurements, which we should minimize and get rid of. But we have the potential to improve on this. And now final question is to theory. I mean, what could this be? I mean, are there any mechanisms within standard model or beyond standard model which could lead to a sudden loss of the coherence in the B0 bar system before the first B decays? So curious and to find an answer. Thank you very much.
Thanks, Hans-Guenther, for the nice talk. Are there any questions?
Sorry if I missed it, but I don't understand why now it's possible to measure the Belle inequalities with Belle 2. Like, what is the advantage that can lead you to allow this Belle test?
Oh, it's just, I mean, I would like to demonstrate it for a heavy system. I mean, now for the time being, it has only been measured for photons.
No. My question was, what is the what change in Belle 2 that now allows you to test the Belle inequalities that wasn't there in Belle?
Better vertex resolution. We are, I mean, we can can use this picture. I mean, with Belle, we have no access to this time here. We cannot measure the time between creation of the B0 bar system and decay of the first B0. And with Belle 2, we have the chance to measure also this time here. And this gives us an additional constraint, and so we can distinguish models.
But will be there in, so it's just a question of cutting on the time. It needs to be a cut long enough that you have space time.
Certainly to cut on this time, and then we can demand that this has already undergone some randomization.
But sorry, you showed the table before where you were showing that the number that should be larger than 2 if you can.
Yeah. This is if you have no measurement.
Okay, if you have no measurement.
If you introduce a measurement on T1, you can somehow, by restricting the data, of course, to a small fraction, because most of them have decayed before. But in principle, you have the chance to do.
And they should have enough statistic even applying this.
Okay.
Thanks for the very nice talk. Probably asked you, but I'm always confused, Brit. So sorry, I would ask again. In your conclusion, can you go to the conclusion? So I'm just trying to understand how the analysis was done in Belle. So here you say that the Belle analysis basically excluded, say, local hidden variable theories, right? Scenarios. This is the main.
No, it excluded essentially the spontaneous. I mean, it excluded essentially 2 models.
Yes.
You can imagine other models, which
these models are kind of like, it's like saying specific models for local hidden variables, and you can exclude them, right? But I mean, what exactly was done in the analysis? Was these models being excluded, or was it also explicitly measured Belle inequality? I mean, you see my question?
No, I mean, the Belle inequality, I mean, this analysis, they use the time propagation of these models,
Mhm.
fitted them to the data, and depending on the quality of the fit, they could say this is favored or disfavored with a certain
Okay, I see.
sigma.
Okay,
And it's not a, I mean, it's not a kind of Belle test anymore, which is much more general and would really exclude any hidden parameters and things like that, but that we cannot do.
okay, this answered my question. Thank you.
Sorry, I come back to the questions that was made before because I didn't understand the answer. So in Belle, you couldn't, there is a strong correlation due to the short lifetime,
Yes.
right? So why the addition of measuring the T1 should allow you to measure the inequality?
Come back to this picture here. I mean, if we don't measure P1, most of the B zeros decay shortly after creation.
Mm.
And this creates this high degree of correlation between the two B zeros and B zero bar. If we ask or force this time to be much longer, then it will make a complete circle and essentially sample the whole phase space. And then it's completely random, like in a photon experiment where you don't know anything about the original polarization of the photon system, and then it could work.
Okay. I see.
More questions? I have one myself. So as far as I understood, you don't have the lean blood type of a decoherence where you emit an extra photon or something.
This is not yet tested, and we still have to do the calculations.
And this would, this is like the branch refraction is enough that you need to
Yeah,
introduce this.
I don't know. I mean, on phase, if you just say, okay, you have a B0 bar and somehow soft photon, you have an additional vertex in your diagram,
Right.
and then you have a suppression of 10 to the minus 4.
Mhm.
So, but who knows?
Right, and this soft photon would have to be somehow not changing much the back-to-back
No, it's
kind of the
20 MeV. This is nothing, and this we would also not be able to see in our calorimeter.
right.
It's just noise, but it would be there, and we would have a quantum number and change the wave functions.
Any more questions? If not, let's thank Hans-Guenther again.